Okay, good morning, everyone. Couple of things that I want to just touch base on. So we did chain rule yesterday. There was homework, but I'm going to be checking homework on Monday. Okay. Today we're going to do implicit differentiation, which is really the last topic of Unit 3. So Unit 3 is just more of like a continuation of Unit 2. This is the last section for Chapter 3. Oh, can you crack the door open? Thanks. And then we're also going to have homework, but I'm going to check it on Monday. I had you guys just pick up another worksheet, review worksheet for tomorrow's quiz. So if we have time at the end of class, we can do some of it, but maybe I think it's good if I just leave it so that you guys can have a fresh new worksheet to do at home, because I feel like if you can do that quiz review from scratch and feel good about it, you should feel good about the quiz tomorrow. So I think that maybe that's a good way of gauging where you are. But you can also wait for me tomorrow to do the quiz review with you. I provided the key for you, so you guys can do your work. So you guys can also check your work. There is a correction, though, that I want to point out is on your the worksheet that you just picked up. It's corrected on the solution key, but I think it just corrected until I worked it out and realized that this number wasn't a good one for problem. So the very last page there, part J, you see t equals 2. That doesn't quite work out for the problem. So if you guys can change that to t equals 1, it's correct on the solutions key. I just didn't get a chance to catch that before I made copies. Everybody good? Okay. Okay, a couple more things I want to point out is that I've been sending. I love Remind. I love being able to send announcements and be able to schedule announcements and send it out. But I don't know if they're gonna change it. But now this year, for some reason, Fulton County is not. They're not, I guess, paying the full amount for the services of Remind. So there's a cap, and so once Fulton County reaches that cap, we can't send out any more announcements to classes. I can still send out messages to individual students, but I just can't send it out to class. So that cap was hit yesterday. So I can't send out any announcements for the rest of the week until Monday. So so I'm trying to figure out what to do with that. So maybe I'll try to work Canvas into it, but it's just something that I have to figure out what to do. But in the meantime, so for tomorrow, the help session is going to be at 7:15. Obviously, I'm not going to be able to send out a reminder about that. But I know that some students like to join online virtually, so I'm not going to send. So what I'm going to do is this. I'm going to make sure this shows up on the video here. So if you go to my website, and hopefully you guys have been using it for checking your work and videos and stuff and things like that. On the chapter 2 page, there's that 2.3, 2.4 quiz, and then I'm gonna put those keys up. You guys have a physical copy of the key, but I'm also going to put it on the website. Here at the very top, you see that Teams link for morning review. So if you want to join tomorrow for the help session, you just go here and then I will make that link live so that you guys can click on it and it'll take you to the Teams link. Okay, I'm not going to be able to send out a message through Remind. So you just have to go there if you want to join in for the morning help session. But it's still here in person, but for anyone who wants to join virtually, I'll make that link live right at 7:15. Okay. Let's see. Okay. Also, I like to be able to send out reminder on weekends because I'm going to be checking both these homework assignments on Monday. But obviously I'm not going to be able to send out that remind on Sunday. So I'm at the end of class, let me ask you on your phone just to put a reminder on your phone Sunday afternoon to check the calendar and finish the homework if you haven't done it already. Okay, so I'll remind you at the end of class today to put a reminder for yourself on Sunday. Okay, I'll be checking both homeworks, 3.1, 3.2 on Monday. Okay, so let's do our lesson for today, and we can continue to maybe touch up on review. And normally I would want to maybe do a little more review with chain rule, but I'm going to just jump directly into today's lesson. Just want to get all the new things out of the way, and then we can worry about the review later on. So this is page 9 in your packet. Give me 1 second, guys. Okay, so so far, when we find derivatives, they've all been nice functions. So what I mean by that is everything we've been working on derivative-wise have all looked the same on the left side. So just to, I know we haven't done these problems yet, but if you look on page 3, for instance, right, these are all chain rule problems, but all the equations have y equals, right? Y equals, y equals, y equals. That y is never mixed into the right side of the equation. And whenever we find the derivative, we only focus our attention on the right side. We never thought about, oh, wait, maybe the left side needs some work too. It's just been notation, right? Y becomes y prime, g becomes g prime. We never thought of the left side as anything that is calculation wise or calculation. It's just a notation that we went through, and our focus was on the right side. Okay, so that's the nice thing about functions is that it's going to pass a vertical line test. And we're able to not have any issues because the y didn't get in the way. It's y equals there's that 1-to-1 relationship. But now we're going to be dealing with equations that may not have that nice relationship with x and y. So first was we have these explicit equations. That's what we've been working with. These are nice functions where it's just y equals, right? And these are what x's and y's are separated on different sides of the equation, and there's nothing done with the y's. You don't see any y squared or square root of y or y cubed, anything strange with y. It's always just y equals. Now, implicit equations are equations where x and y's are mixed together, like this, where something is done with a y variable, or there's multiple y's showing up in the equation. These are usually not functions, so these will not pass a vertical line test. But even though they're not functions, we can still create a slope formula for these graphs, right? I mean, they could be graphs that look like this, right? Where obviously it doesn't pass a vertical line test, but we can still create a slope formula that can tell us the steepness of every point on this curve. So that's what we're working with. We're working with equations now that are not necessarily functions, but they're still curved graphs that, and we can still create slope formulas for the curved graphs. Okay, so let's start with an explicit equation first that we know how to do. Okay, so we want to find the derivative. So we are let's worry about the left side, which is called it what? Y becomes what?
Y prime.
Y prime. Okay, y prime equals, and then go through your derivative power rule process. What would you get?
6x
6x
minus 27x in second.
And then the 5 goes to 0. Good. So we did power rule on the right side. The left side is really just notation. I want to show you that technically we are doing power rule on the left side, because y to the first power becomes 1, and we're indicating that y becomes y prime. So in other words, we can also think of it as this way: y becomes 1 because if x's derivative is 1, then y's derivative is also 1. But because we're asking for y's derivative, another representation is dy dx. Now, y prime and dy dx are the same thing, but I'm going to see if we can transition over to dy dx when we do implicit, because this is more descriptive, and sometimes y prime can be thought of as y to the first power, especially when it's mixed into the equation. So I just want to show you that technically we are doing the derivative. Y's derivative is 1, but we need to attach the dy dx. So that's what is happening here.
Okay. What does dy dx allow you to do?
dy dx, it means the same thing as y prime. It's more descriptive because it tells us we're finding the derivative of y with respect to my independent variable x. It just gives us a little bit more detailed information than y prime does. But if you want to do y prime, it's fine. But I'm going to do dy dx especially when there's multiple y's in the equation. Okay. So that's what we're going to do with when we see implicit. The first thing is to recognize that there is something a little strange about this equation, right? And if you see anything done with a y variable, you know that there's going to be something that we have to worry about with the y's. Okay, so let's just go ahead and find the derivative like we normally would. But I'll show you what additional step we got to take. So what's y squared's derivative?
2y.
2y. Now we took y's derivative, so we need to attach something else, just like on this side, right? Y becomes 1, but we need to attach a y prime or dy dx. So every time you take a derivative of y, you need to make sure you indicate you are asking for y's derivative with respect to x. Okay, 5x becomes
Minus 5.
minus 5. And then 4 goes to a 0. Now, some students had the question of asking, wait, so if there's something special with the y's, how come there's nothing special with the x's? And technically there is. Okay, so I'm going to write it a different way here. So 2y dy dx. We are finding the derivative of x with respect to x, but it ends up being 5 dx over dx. And the dx over dx is just going to wash out because we're finding the derivative with respect to itself. There's not going to be any leftover thing to worry about because it just turns into 1. So that's why if x is the independent variable, we never have to worry about, oh, I need to do a d over dx, because that just washes out. It's only the dependent variable that is going to have some leftover variable that we got to keep track of. Okay.
Why is one of them dy over dx and the other one dx over dx?
Because this is asking for the derivative of y with respect to x. So there is that relationship that we have to keep track of. It's not just going to be equal to 1. But dx over dx, if I'm finding the derivative of x with respect to itself, it's just going to be 1. So there's not going to be any leftover thing to worry
So it's
about.
not like with respect to y.
It could be, but for our course, typically, x is our independent variable. Y is usually not the independent variable.
Okay.
Now, we may have times, we're going to see in the, later on, where we have other independent variables like time. But for us, we should basically have to worry about, the only independent variables we're going to see in this course is x and t. T for time, and x is our independent variable. Okay, so we're done with the calculus step. You know how before we never have to worry about solving for dy dx because it's always just by itself, right? We never have to worry about, okay, I got to separate dy dx from the rest of the equation because y was always by itself. It just produced its own derivative and the variable is just by itself, which is nice and clean. But this, if your y is mixed into the equation, your dy dx is not going to be isolated. So our cleanup step is just trying to isolate that dy dx. So the calculus is done. We're just adding, subtracting, dividing to find a way to get that variable by itself. So how would you move things around to get that dy dx by itself? Yep, let's move that 5 over first.
Divided by 2.
Close to y. Yeah, you want just that dy dx by itself. Even the y's, we want to move over to the right side. So my derivative equation is 5 over 2y. Now, this feels a little bit strange because typically our derivative is in terms of x, but now our derivative is going to involve the y variable as well. Okay, because our equation is going to look a little different.
So it ultimately goes to dy dx by itself.
Yes, which is the same thing as y prime. Basically, this is a slope formula. So if I want to find the slope of this graph, whatever this graph looks like, I should need to provide it the information. Sometimes it needs the x and the y. Sometimes it just requires the y, but the derivative now needs more information. And the reason why it needs more information is because it doesn't pass a vertical line test. So for instance, let's say I want to find the slope of this equation at x equals 2. But if I just give it an x value of 2, the slope, the derivative is going to be confused because it doesn't know what value you're talking about. Okay, are you talking about this point or talking about this point? Because they may have different slopes. So that's why your derivative may require both the x and y value because there may be some overlaps and it needs more additional information so that I can pinpoint what point you're talking about. Okay. But we're going to treat this the same way. Okay, this is just a slope formula. You give it information, in return, they'll spit a number back to you, and that number will correspond to the steepness of this point on the original graph. All right, so let's go ahead and try example 1. So really, the key thing here is as soon as you involve a y's derivative, you need to attach a dy dx. So sometimes you may have multiple dy dx's that show up, but it's okay because from there we can just algebraically try to solve for dy dx. But for x's, don't do anything special. X's, just take the derivative like you normally would and just move on. Okay, so example 1, x squared minus 2y cubed plus 4y equals 2. You see something strange about the y's. If you see something strange about the y's, you know there's this implicit differentiation going on. It's not going to be a function, but we can still find the derivative. Okay, every term is nicely set up for power rule. There's no need for any messier rules like product, quotient, or chain. So let's just jump into our derivative. X squared becomes 2x. 2y cubed becomes
minus 6 minus 6.
Okay. Now there's something special we got to do here. Anytime we do y's derivative, we need to attach
dy dx.
dy dx. Again, you can also say y prime, but I'm going to do dy dx. I find that to be more descriptive. Sometimes y prime can be misinterpreted. So, okay, everybody good so far? Okay, what's 4y's derivative? 4
dy dx.
Good. We are asking for y's derivative. Even though the y disappears, a dy dx will still show up. Equals what? Now, good. Both sides of the equation are impacted by the derivative process, not just one side. So make sure you remember that if I have a constant, that constant is going to go to 0. Both sides of the equation is getting impacted by my derivative process. Okay, any questions here? So this is the only calculus step here. The rest of it is just cleanup. We basically have the slope formula. It's just a little bit out of order because our dy dx is not by itself. Okay, so what we're going to do is we're going to try to group or collect the dy dx terms together on the same side. And then I can move the non-dy dx to the other side, and I can factor dy dx out, and I can then solve for dy dx. Okay, so first thing I'm going to do is I'm going to try to get these two together on the same side. They're already on the same side, but this 2x is out of place. So I'm going to move all the terms that are not connected to dy dx over to the right side of the equation. So now that the dy dx's terms are together, I can do what? I can factor it out. Okay, factor it out. There may be other factors, but don't worry about them. You just want to get dy dx by itself. So just factor out the dy dx. Okay, what's left if I factor it out? Mm-hmm. Right, we're almost there. To get my derivative variable by itself, I can just do what? Divide. Okay, so here's my slope formula, right? It requires a bit more information because it doesn't pass a vertical line test, so it needs to pinpoint, if there's conflicting points above each other, it needs to know which point you're talking about before we can find the slope.
Any 2x's and do you divide minus 6y squared plus 4 over the or something?
Yeah, so I divided this whole parentheses over to the other side, so it ends up in the denominator. Yeah.
Would you simplify that or?
You could. I'm not going to require it, but yeah, you could. I do want to show what you could do. So you could take out a 2 from the denominator. And then you can take out one of the 2's here, so negative x over negative 3y squared 2. I think it's still a good skill to do in terms of reducing, even though I'm not going to require it, because on the AP exam, if this was your answer, they would work it all the way down to here, or some version of this.
So top and bottom's negative, would it stay like that or would it go to positive?
It would stay like that, yes. We can't take the negatives out because this is attached to another term by addition. Now, I do want to point something out here. Another variation that you could see is sometimes they do this. They would multiply everything through by -1, which is the same thing, right? I'm multiplying basically by 1, but that means your equation may look a little different. If I distribute everything through here, then it becomes 3y squared minus 2. And it's just nice to know that if you're looking, if this is what you arrived at and this was the answer choice, you can still get from here to here by multiplying the top and bottom by -1 and seeing if that will create a different version of your answer. So this is just skills for matching with multiple choice. But if it's pure response, right, this is okay, this is okay, this is okay. Right.
Or do they want you to simplify it?
Hmm?
They want you to simplify it?
Yeah, so on the AP exam, you can, as long as your answer is a version of their simplified version, they will accept it. The only thing, though, that I want to point out is, if this is kind of like a side note here, but if your answer involves like a trig value, you can't leave it like this. You got to go all the way down and show the numeric value associated with that. So this you can't leave alone. But typically, anything that is if it's not reduced, they will accept it. But still good to know how to reduce in case you're trying to match with the answer choice that is reduced on the multiple choice section. Okay, any questions so far? Now, I do want to point something out here. Sometimes I see students do this where they only attach a dy dx if they see a y. But we don't want to make that conclusion because sometimes there is no y here and you still need a dy dx. So I think the safer way to think about this is that if you want to count how many instances of y's in your original equation. So here we have 2 instances of y's. So to find the derivative, you're going to produce 2 dy dx's. Okay. Sometimes I see students, they don't include dy dx here because they see, well, the y is gone, so I just leave it as 4. Okay. And also, we only want to attach dy dx if there is a derivative going on, right? Just because you see a y doesn't mean that you're applying a derivative. So count how many y's you have in your original equation. That's how many dy dx's will show up in your derivative step. Okay, let's go to the next page here. Okay, 3xy cubed minus 2y equals 7. You guys see a need for implicit here. Yes, why?
It's the x and the y. There's 2 y's.
Yeah, there's or something done with the y's, right? Even if there's only one y here, that y cubed is a kind of a it's kind of a giveaway that, oh, there's something, something's done with the y's. I got to do implicit. Okay, I got to keep track of my dy dx's. Good. So we know we have 2 y's, which will produce 2 dy dx's. Now there's something else going on here. There's another procedure that we have to involve besides just power rule.
Is the x and the y already over? So.
Yeah. So what rule is that? Product rule. Yeah, we got to do a product rule here. It doesn't announce itself, but we need to recognize the need for product rule here. X and y cubed, they're being multiplied. I can't merge them into the same variable. They have to stay separate. And if they're staying separate and they're being multiplied, and I want to find the derivative, I got to go through a product rule. So I'm going to label that as f and g, and I'm going to apply product rule there. And then I can finish off the rest of my derivative. So all this is just for that 3xy cubed. I'll worry about the negative 2y equals 7 later. Okay, so 3x is my f, y cubed is my g. What's my f prime going to be? Just 3, okay. My g function with y cubed. Do I attach a dy dx here?
Yeah.
The answer is no. Do you know why?
Okay.
Because it's only asking for what? G. It's not asking for the derivative, right? We only attach dy dx if it's asking for the derivative. But this process here, this g is only asking for g, so we just copy down the y cubed. We don't do anything more to it. Okay. Okay, back to f. X. G prime. 3y squared. Okay, now we're doing y's derivative, and then we can do what? dy dx. Does that make sense? Sometimes your y variable doesn't include dy dx because the process doesn't ask you for the derivative. But if it's asking for the derivative and there's a y to begin with, then you need to make sure a dy dx is part of your variable.
So if you do power roll, then it's basically your thing.
I'm sorry?
If you do power roll, like you say some dy dx.
If you do power rule and there's a y
And there's a y.
there, then there'll be dy dx. Yeah. I know right now we only have to learn power rule, but later on we're going to have other derivative rules, and other derivative rules may produce a dy dx too. But basically, if there's a derivative involving a y, make sure that you attach a dy dx. Okay, keep going. Minus 2y becomes, what's negative 2y's derivative? Good. Negative 2, right? A linear goes to a constant, but we are asking for y's derivative. Even though the y disappears, we need to have a dy dx here. Equals 0. Good. So sometimes students forget that the constant on the right side is also impacted. Okay, so the calculus is done. You've earned the majority of your points here. And now the rest of it is just trying to do what?
Solve big dy dx.
Yeah, get dy dx by itself. Okay, so I have two things that are attached to dy dx. I'll leave these on the left side. I need to move my non-dy dx terms to the right so I can factor that dy dx out. I'm going to clean some stuff up along the way as well. Okay, what's next? Factor dy dx.
But how do you get to that first part? Like, do you like multiply the terms together?
Yeah, that's right. Yeah. So I want to clean this up a little bit. The 3 and 3 can multiply together, so I made it 9xy squared.
What did it 3y? Or you brought it over to the other side?
This is being multiplied, so I don't have to. So this is attached. This is all connected. The plus sign indicates that's a separate term. I can move that over, but I don't. But I don't want to move this over. I want to just clean this up a bit before, because this is. I want to use this. Think this as one connected thing until it's ready to move. Okay, final step.
Bring over to 9xy minus 2.
In its denominator, right? Divide it over. Yeah.
You can make it so it's minus y cubed to 3xy squared.
Okay, sorry, say it again.
Oh, sorry. You can like simplify the coefficients, make them like make it minus y cubed over 3xy squared.
Okay, we gotta be careful there. Why can I not do, I can't do that. But yeah, that's subtraction there. Is preventing us from doing anything with this. Unless you can factor it out from both sides. Now, if it was missing that minus 2 there, then it's great. You can take out the 3 and 9, you can take out the y's. But as soon as there's an addition and subtraction there, we're stuck. We cannot, because if we cancel out, it's not the same value. It's not the same fraction. Does that feel weird?
That makes sense now. Yeah.
Yeah.
I just gotta make sure to look for the signs, you know, if it's on like a different side of the.
Yeah, so, well, it's because it's anytime there's addition and subtraction with fractions, you got to be careful. We cannot cancel out. Yeah, so as much as you would like to. Now, if there were no multiplication here, if the 2 was being multiplied with a 9, then yeah, that's great. You can take out anything you want. But yeah, make sure you don't cancel across the addition and subtraction. Okay, good. Any questions? Okay, if you guys can turn to page 12, I just want to show you how we can also use the derivative with implicit to find the slope. So I know we're not seeing everything here, but I just want to show you enough before I'll have some time to do some review. So this is page 12, number 24 here. Now let's read the direction here. It says, find dy dx by implicit differentiation. Okay, even if they didn't tell us the instruction, we should be able to know when we're going to involve implicit because we see something strange with the y's, where the y feels out of place. That's how we know there's implicit. And evaluate the derivative at a given point. So we know that a derivative using implicit is still a derivative. It's still a slope formula. I can still insert order pairs or information about the point, and in return, it'll spit back a number, and that number is still corresponding with the slope. So I want to show you that, we still find slope the same way. We just plug in our information into our derivative. So for 24, how do we know that we need implicit here if I want to find the derivative?
The y and x are the same side.
Yes, and also because there's something done to the y's, right? Normally it's y to the first power, but here's y raised to a power or a radical involving y. Okay, but we know we can do power rule for each term, right? So derivative x to the 2/3 becomes
2/3 x minus 1/3.
Y to the 2/3 becomes
2/3 y minus 1/3.
good, dy dx. And the 5 goes to a 0. Okay, so the calculus is done. We just want to clean this up and solve for dy dx. Now, I like to deal, it's easier to think in terms of positive exponents. So let's just go ahead and push those variables back down to the denominator. And I'm going to move it, maybe it's too much. I'll do one thing at a time. Okay, I'll subtract this fraction over to the other side. Okay, any questions so far? So I want to solve for dy dx. This is still here. So dividing a fraction feels messy, right? But I can do something else. Dividing by a fraction is the same thing as what? By the reciprocal. So that just feels a little bit cleaner. That way I have to look at a fraction underneath another fraction. I could just flip it and do multiplication. Now, a lot of this can cancel out because you see that everything here is a multiplication relationship, right? I can cancel anything between numerator and denominator and not cause any issues, right? So all this can go away. So this derivative cleans up very nicely. Negative y to the 1/3 over x to the 1/3. So this is the slope formula, whatever this graph looks like.
What's the point for it? I need that.
I'm sorry?
What's the 8 to 1 point coordinate for?
Oh, that's for us to find the slope. Right, so it says, after finding the derivative, evaluate the derivative at the given point. So,
So we only do like one part of the problem.
right, so now but the second part is pretty straightforward. We're just plugging in, right? This is asking, okay, at the order pair A1, what is the slope looking like? What is the steepness of the graph? Well, we have our slope formula. We just have to plug that in. So now there's a notation to plug in if there's an x and y. Typically, if it was just a function, we would just say f prime of 8, right? But in this case, we need both the x and y value. So the way that you would represent that notation, maybe I'm running out of room here. You're going to write it this way. And just also good for notation here. dy dx, you're going to say dy dx, you're going to put a vertical line here. And then you're going to say 8, 1, because you realize that the derivative requires both the x and y values. So this means the same thing as f prime of 8. It's just that we're no longer dealing with a function and it requires both the x and y value. But this just means that I'm going to take this order pair, insert it into the derivative, and get back the slope value in return. So negative what?
Negative 1 to 1/3.
Yep.
Or 8 to 1/3.
Yep. Now, 1 to the 1/3 is 1, and the negative is going to have to stay there. Okay, what's 8 to the 1/3? Good, that's cube root of 8, right? Cube root of 8 is 2, so negative 1/2. So this tells us that whatever this graph looks like, at the order pair 8, 1, the graph is going to experience a gradual negative slope of 1/2 or negative 1/2. So
Is there ever a time where it's like not gonna be like exact? There's so many like variables in.
no, if I'm trying to find the slope, I should be able to replace every x and y value with a number, and I should be able to get only a number in return. Okay. And then obviously, if I want to take the next step and write the tangent line equation, I can just take the order pair, take the slope, point slope form. Okay. Any questions with implicit? I do think, let me just point something out here. We did this already, but the most challenging thing about implicit is sometimes it's hard. So I think it's easy for students to recognize the need for implicit, but sometimes it's hard to spot product rule because it doesn't announce itself, right? So you see X and Y. Sometimes I see students, they just say, oh, okay, X derivative is 1, Y becomes dy dx, and they're done with it. But you have to be able to spot the need for product rule. And sometimes that's a little bit, that takes some time to get used to, especially if the problem doesn't say, hey, do product rule here.
So like you can do the product rule and then once you like get the derivative of them separate, you're allowed to put them back together.
Uh,
The other one. Sounds like.
yeah, so like this one, right? You have multiple dy dx's, but ultimately in the end, you're going to factor one dy dx out. And then it's just in the end, you're only going to have one dy dx. Is that what you're asking?
Because like the X and the Y combined again after you separate. Right.
Yeah, so I mean, if there are like terms, then we can combine it, but if there's no like terms, we kind of have to just leave them all kind of separated.
How did you do the example 3 one?
Yeah, so that one is a little bit, it's kind of a connector into the next section, so we'll leave that off for now. Okay, I'll come back to it when we get closer to the next unit. Okay, so there is homework for this, but I will check it on Monday. I just want you guys to focus on the quiz. So we worked through a good portion of the packet, the back page of that packet, the quiz review. So page 46, we got all the way down to G and H, right? Okay, so 2 more here. Is the speed increasing or decreasing at t equals 4 and justify? So what's our strategy for determining increasing and decreasing speed?
Velocity, sorry.
Yeah, we look at velocity and acceleration. And in this case, we're going to plug 4 into both of them. So plug 4 into velocity, I get -9. Plug 4 into acceleration, I get 6 feet per second and feet per second squared. So what does this tell us? Speed is what? Decreasing.
Opposite sides.
Yep. So I want you to specify what has opposite signs. So you can say v of t and a of t have opposite signs at t equals 4. Or you can say v of 4 and a of 4 have opposite signs. Either way, but just indicate to me what has opposite signs. If you just say they, I may take a point off because I want to be more specific. Okay. All right, J is something that trips up students as well. Is velocity increasing or decreasing at t equals 2? What do we look at there? Not position, not velocity, but what? Acceleration. Reason why it's acceleration is because we see the word increase, decrease. It's talking about the rate of change of velocity. So it's asking about the function below it, which is acceleration. So what's acceleration at 2? -6 feet per second squared. So we're just basing our conclusion on this number. This is a negative number, so that indicates that velocity is what? Decreasing. Because acceleration is less than 0. So you can imagine why this is easy to get thrown off. Okay, we didn't do the first page, so maybe we can do a page 45 of it.
was gonna look like just like this.
Yeah, more or less. Well, I think it's actually gonna look a little bit closer to the worksheet 3 that you picked up. So, but it's, very similar.
No bonus or?
No bonus. Okay, so for number 1, did we do number 1 together? No, okay.
No, we haven't done this one. This one.
It's the whole paper. Okay. So guess what we can do? We can use for the entire X function here. We just rely on what? Just power rule. Yeah.
There's pi in the.
There's pi, right? But pi is just a number, right? Pi is not a variable, it's just a number. It's 3.14. So okay, so I can distribute everything through distribute at 7 cubed. There's no need for product rule here. I can distribute that easily. How can I rewrite that 3x squared over 11 to make it feel like it's ready for power rule? I don't need quotient rule for that. It's ready for power rule, but it just feels a little strange with that. So what can I do to make it maybe a little cleaner?
11 to the -1.
That's too messy. You don't have to, but I find it cleaner. What can you do to rewrite this to make it look more like what we have here? Yeah, 3 over 11x squared. I mean, it doesn't feel like a big deal, but I just don't want students to feel like, oh, they got to go through quotient rule when they see that 11. It's just a coefficient in front, just like a 7 or 9, but it's just somehow it's just a fraction. Right. I'm just in my cleanup process. I'm not doing anything with derivative yet. I want to make sure everything is ready. How would you write this? X to the 4th. What's this here?
X to 1/7.
I think that's what a lot of students want to say. They want to say 1/7, but it's not 1/7. 7 over 2. 7 over 2. So now
you bring it up to.
Yeah, you bring it up too. So now I can see why this causes so many issues, right? Because we want to say 1/7 or we want to say 2/7, but it's actually 7 over 2. And it comes up as -7 halves. I think the cleanup process is the hardest part. Now let's go through power rule, right? So now we can go through power rule, bring all the exponents down.
Replace y with dy dx.
Well, no, we don't do that here because we're not doing implicit. The y's are not out of place, right? So there's no need to do that if the y's are out of place. And also, you won't see implicit on the quiz.
On test we will.
Yeah, the test you will.
You said pi is just like regular number.
It's just a number, right? Pi is like 3.14. So what do you think the derivative of 5 pi to the 4th is?
I think it's 0, but.
It's 0, yeah. So some students, they do 20 pi to the 3rd power. They treat it like power rule. They treat the pi as a variable, but it's just some number, right? So 5 times 3 to the 4th power is just some large number. It's still a constant, so constant will still go to 0. Okay, so 7x to the fourth becomes 28x cubed, 7x cubed becomes 21x squared. 3/11 x squared becomes 6/11 x. 4 pi x becomes 4 pi, 5 pi fourth becomes 0. X to the 4th fifth becomes 4 fifth, x to the negative 1 fifth. And then 5x to the negative 7 halves becomes negative 35 over 2x to the negative 9 halves. So if you get to this point, you've earned the majority of your points. The rest of it is just cleanup. Any variable that still has a lingering negative exponent, you want to bring it down to the denominator.
Okay, so, that's how you earn all the points.
Yeah, so I'm gonna say, at the top of the page, no negative exponents.
Oh, okay. Let's say like we forget, yeah, well, you still give us the majority of the points.
Yes, now that's a minor, that's minor. The most important thing is getting the set. Okay, I didn't provide a key for this, but I will put a key for this on the website under today's date. You guys do have a new worksheet. You guys, if you can get through that today, afternoon, evening, you should feel good about the quiz, but I'll still be available tomorrow for so, okay, go get your phones.
Thank you.
I'm subtracting one from the exponent, right? So what's negative 7 halves minus 2 over 2? Negative 9 over 2.
Then you did four.
I'm
studying.
the stop sign.
Yes.
Yeah, this is already the derivative.
No, it's really, I.
This one yesterday, I'm like.
Yeah, so this is chain rule. We'll go through that later. This is a
Okay.
little, this is also a complicated process,
All right.
but not on the quiz.
Okay, so we'll go over that like Monday.
Yeah, I think that's a good day to do it.
Don't feel shy. It's like $50 on it. And
Have a great day, guys. Study for your quiz.
I feel like I'm in that direction, but it's kind of like. I
Yeah,
feel bad.
no, no.
Yeah.
As long as you're available for me for when I need you, I'm.
Okay.
I think Monday, I need your help too. It's great. On Tuesday, it's 30 minutes. Great. So,
Yeah,
yeah, as long as you're available for me.
all right, thank you.
Okay, thank you. Okay, have a good day.